So let's recall the tricky example from part 2, talking about the regular comparison test. The limit comparison test is a really nice way to do this example. The limit comparison test codifies, and it makes it a little more precise, the idea that we usually start with when we're thinking about the comparison test is that these terms, when k is really big, these are basically like, I just cannot write 6k very well, can I? Basically like 1 over k squared. And even though this makes the denominator a little smaller, and therefore this fraction a little bigger, still they're very similar to 1 over k squared. And so the behavior when you sum these things up should be the behavior when you sum these up, and that converges. Okay, and that's what we can do much cleaner than what we saw with the regular comparison test. So the limit comparison test says that if you have two series, sum a sub k, sum b sub k, it's still positive terms because we still are talking about just does it converge based on big or small, and not about wiggling of the partial sum sequences. So I'm going to put that in with a sub k. I'm going to use k's now. I really do prefer it. And here's what we're going to assume is that in the limit, comparing them is a good way to compare these numbers in terms of sizes is look at the ratios. If this exists and is greater than 0, so it exists as a positive number, then either sum a sub k and sum b sub k both converge, so they do the same thing, or, and I've run out of room, or they both diverge. They just have the same behaviors, basically. So this is much slicker, that as long as you just calculate this limit, and if it's a finite limit and doesn't go to 0, so that they're of the same order of size as a sub k and b sub k both go to 0, and so that's just a limit about the terms, then as long as you can figure out that limit, then you can say that these summations have the same behavior. Either they diverge together or they converge together. So here, let's see, I hate to erase the stuff, but okay. So here, we would just we'd still do the very rough intuition of like, well, what should I compare it to? I still need something to compare it to. But I'd still focus on the higher order terms. And I would say, let's look at the limit as k goes to infinity of, this would be our a sub k sequence, the sequence we're interested in, and then divide it by 1 over k squared. Oh, in other words, I'm going to multiply it by k squared. Oh, hey, this is exactly the kind of limit we're good at as going off to infinity, and it follows the same intuition. We know that we can ignore the lower order terms. That's equal to 1. That is a finite limit. It exists, and it's greater than 0. So, and we know, and why this is useful, we know that sum of 1 over k squared converges. And not working too well. Converges. So this more complicated one converges as well. Much quicker, much simpler. So this is very powerful. You still need to have the same kind of process at the start. Look at it roughly, get a sense of what the terms are generally doing, strip off stuff that seems to not matter to get an idea of what you're going to compare it to, then calculate this limit. Now, if you calculate that limit carefully, that limit doesn't exist at all, maybe because there is some sort of uncontrolled behavior in terms of the ratio of the sizes, then you're out of luck. If this goes to infinity, you might be able to say something, but well, I'll do that in the second part video. If it goes to 0, you might be able to say something, but your best situation is when you've picked out the comparison correctly enough so that this limit does exist as a finite positive number. That's a good indication that you really are comparing it to something that it's really comparable to. And so we'll look at some of the subtleties in another example.